we are looking at what we're looking at, 2 oxygens. I'm going to draw the aldehyde out. I'm pretty sure this was a quiz question.
This was definitely a book problem too.
It's definitely a book problem, and I'm pretty sure this was one of your quizzes. Because on the quiz I forgot that oxygen, you had to call me on it when I went over the key. A, B, T. So this would have been quiz 10, I believe. I think would have been the second quiz after the exam, and I think there were 8 quizzes before the first exam. So a synthesis of ketone C, central and temps of blah blah, who cares? Anti-tumor agents, start with aldehydes, and anything else you need. Provide structures for the key intermediates. As usual, the secret to success is counting carbons, so you actually know what's going on. Probably safe to start with this oxygen in the ring. Chances are pretty good the carbonyl group is still a carbonyl group. And obviously, that carbon is that carbon. So the new bond is between the carbonyl carbon of A and carbon 4 of B. So what that means is it's a Michael addition. And this has to be the nucleophile. Right, because this is electrophilic, and we can draw the resonance structure that shows us why by applying great rule of organic chemistry number 1, which always works, which tells us that there's a significant positive charge on carbon 4. So it's a 1,4 addition, and I cheated. I numbered this oxygen 1 so it would look like carbon 4 was getting attacked. It's a 1,4 addition if you consider the carbonyl oxygen to be the 1 of the pi system. So what we need is an acyl anion equivalent. And because it's unsymmetrical, we can't use the thiazolium salts. Thiazolium salts only work for combining 2 aldehydes when it's the same on each side to make alpha hydroxyketones, and that's not what's happening here. So we need a dithiane. So the first thing we need to do is take compound A and convert it to the thioacetal by reacting it with 1,3-propane dithiol and zinc chloride, or some other Lewis acid. So that's a thioacetal, but it's also what's called a 1,3-dithiane. Because it's a 6-membered ring with 2 sulfurs in positions 1 and 3. This is now an acidic hydrogen because of the 2 electron withdrawing sulfurs that are pulling electron density away. So if we use a strong base, we can take that off. And butyl lithium takes that off of there. Make this. As the lithium salt, normally lithium salts, lithium reagents, alkyl lithiums would attack the carbonyl carbon and do 1,2 addition. But this one is a lot more stable because of the electron withdrawing sulfur group, so that makes it softer, which is what allows it to do the Michael addition. And then if I just redraw this molecule so that that carbon is available, that forms our new bond that we were trying to form. Makes an enolate. And then protonation of the enolate in aqueous acid workup to generate the final product. So step 1 is to make the thioacetal. Step 2 is to remove the proton. Step 3 is the Michael addition. And step 4 is the protonation at the end. If you wanted to write the reaction conditions out, just as a pathway, add compound B, so start with A, 4 steps to get you there, compound B being added in step 3.
Is the aqueous acid always need to break the sulfur thing?
Oh, I forgot. Yeah, you gotta take the sulfur group off. Now, to take the dithiane off, you need mercuric chloride to deprotect. So it's not the product, right? It's actually only gets you this far, and then the mercuric sulfide takes you to the rest of the way to the product. If you crush it with enough acid, yes, this does actually come off in an aqueous acid, but usually you get milder conditions if you use the heavy metals, the mercury. It doesn't always have to be mercury. I think lead will also do it. Lead and mercury exist as their sulfides in nature too, galena and cinnabar respectively. So they really, those heavy metals down there in the bottom of the periodic table really like sulfur. How many points was it?
10, that's why.
5 steps. 2 points per step, I guess. Although you could actually have kind of combined these steps as adding B and the aqueous workup. It wasn't absolutely required to show the enolate intermediate. Counting carbons, right? Counting carbons is the key, because that's normally how you identify which carbon-carbon bonds you're making in the product. It's also a good way of making sure you don't accidentally lose carbons in the middle of the process and draw a product that has fewer carbons than it should have. There was some of that on the last quiz. Some people had that isoquinoline ring shrinking from 6 to 5. Yeah, that was a book problem and a quiz problem. I could find it if I wanted. It would be section 23-4, because that's the section on dithiane. that problem came from. That was problem 45 on page 1094. Could we go over what?
The rank increasing acidity on the benzene.
The ranking of acidity, yep. Behave. What the hell? Roll, damn you. Fingers have so much chalk on it that my trackpad's not working. So we want to compare the acidity of the circled hydrogens, rank them in order of increasing acidity, so most acidic on the right. Explain fully the reasons for choosing this order. Please do not only list pKa values, although actually listing pKa values would also be a good idea. So it really helps if you actually know the pKa values of these compounds. So if you happen to know that this pKa is 41, that's helpful. That pKa is 16. And that pKa, because it's on a benzene, ranges around 44. That's a plain old sp3, that's around 50. And this pKa is 39. So if you know those things, then it's easy to rank them from least acidic, which is this one, to next least acidic, which is this one, to next least acidic, which is this one, to the second most acidic, and then that's the most acidic one, or you could write them like this. Basically amounts to the same thing, right? So that's the order of ranking that we know is the order of ranking because we know the pKa values. So now we have to look at four things, right? Resonance, polarizability, electronegativity, the S character. We don't really have to look at those two because all of these are going to be carbon anions. Right? So what we're really doing is comparing the stability of the corresponding anions and determining that this is the least stable anion and this is the most stable anion. And we have to add one more thing, right? Because now, in addition to resonance, we also have aromaticity. And if your anion is aromatic, that's even more stable than if it's just stabilized by resonance. So this is an aromatic compound. This has 7 resonance structures. So even though it's anti-aromatic, and that's what makes it 23 orders of magnitude less acidic than the 5-membered ring compound, it still does allow you to delocalize that negative charge on all 7 carbons. And we can write resonance structures for that if we want by just moving pi bonds around. So you can prove to yourself that it actually does have 7 resonance structures if you're the kind of person that wants to prove to yourself that it has 7 resonance structures. have 7 yet. That's only 6. You didn't really need to show the resonance structure, but I've said in the past that it has 7 resonance structure, and I never actually showed you all 7 of them, so there they are. Okay. So it can actually delocalize onto all of them. That's true whenever you have an odd number of carbons in your ring. If you have an even number of carbons in your ring, like benzene, you can only put that charge on every other carbon. But if you have an odd numbered, you're able to put it on all of them. So you could write 5 resonance structures for this if you wanted to as well. This one has 4 resonance structures. This is the only one of those 4 that doesn't break the aromaticity of the ring. All of the others form that pi bond to the rings. So and that's what I was saying, when you have a 6-membered ring, there's only the possibility of putting it on every other carbon. So fewer resonance structures for this one. There are the 3 others, right, that have it on the ortho and para carbons. This one has no resonance structures, but it does have it in an sp2 orbital. And this one has it in an sp3 orbital. So this one has greater s character than that, and that's what causes that to be held tighter. The sp2 orbital is smaller than the sp3 orbital, which means that the electrons are closer to the nucleus. So it's mostly a resonance argument. The S character is only necessary to explain the difference between the 2 6-membered ring structures, and all the other is aromaticity and resonance. The more resonance structures, generally the more stable. The exception, of course, being this one, right? This one has fewer resonance structures than the 7-membered ring, but because it's aromatic, you get that additional aromatic stabilization energy. The same is true for nitrogen-containing things, right? If this were nitrogen out here, the lone pair on that nitrogen is less basic because of the ability to resonate in the ring, which means that the corresponding ammonium ion is more acidic. And I think we talked about this one, right? We talked about how that is not basic at all. And in fact, if you want to protonate pyrrole, you don't even protonate it on nitrogen, you protonate it here, because that lone pair is already part of the aromatic ring. Where would this fall? So the pKa of the conjugate acid of this which is this structure. Actually, I'll draw it in its most stable resonance structure. That's the most stable resonance structure. This pKa here is negative 4.4. It's a very strong acid. Because right now you have a non-aromatic ring. But if you take that hydrogen off, now you have an aromatic ring. The pKa of this hydrogen is actually not that hard to remove. So normally an NH peak doesn't act as an acid. And I can't remember what the pKa of that is off the top of my head, but we can look it up. .5. And for the corresponding ring that doesn't have the pi bonds, pKa is similar to ammonia. It's around 35. Right, so it makes a big difference when you have that aromatic system on it. S character is generally a smaller factor than resonance or any of the others. When you're talking about the nitrogen-containing bases, though, what you're usually worried about is whether that lone pair can participate in resonance. It's kind of cation stability, right? The more stable the cation, the more basic the lone pair. And the cation is more stable if it's able to resonate around. What else did we have on that exam? Any lab questions? Look at that, there was a lab question. Obviously, I can't ask you lab questions on the Diels-Alder reaction or on the bromination because not everyone has done those two labs yet. But the other four are fair game because everybody's done those. In theory. Has Dr. Thomas already collected the lab report on morpholine? Results in discussion.
We're in group B, so she has for group B. I don't know about group A.
Pretty sure Group B, you guys are doing the Diels-Alder this week, right? Which means Group A did the Diels-Alder last week, which means they're done with morpholine. They were done before you. And you're not doing the bromination lab at all, right? Just slackers. What? No, too late. We already started. Group B has already done the bromination lab. Slackers. I should put bromination lab questions on the exam.
Dad, I'm drawing the line. Line in the sand. Do not cross.
We all know that red lines mean nothing. I mean, we drew red lines in Syria and it meant nothing. We all know that red lines mean nothing, right? We drew red lines in Syria and then we ignored them. Even though you're not doing the bromination lab, you might want to look at the questions at the end of that lab because you should be able to answer those without even doing the.
We don't even have that in our lab manual.
What? The bromination lab?
Like, I'm dead serious. You can go through our lab manual.
Yeah,
We
we
don't
have
have it.
we like different lab manuals, like on our window.
Huh.
So like Thomas will like put on pages that we use.
So she deleted that lab from the lab manual?
Like, we legit don't have it. I'm not making
Huh.
that up.
How about that? She didn't tell me she was doing that.
You can take that up with her because we had no idea.
Anyway, I mean, the questions on the lab manual are basically questions you should be able to answer anyway, which is, right? You're doing this, you're making that from it with acetic anhydride, and then you're brominating it with actually sodium bromide and sodium hypochlorite. So it's a greener condition instead of bromine, which is bromine liquid, just a pain in the ass, which basically generates little bits of Br2. And then it asks you where the bromine's going. Is it here or here? Or here? one would you expect to be the major product?
First one.
First one, why?
The ether is activated.
I didn't ask that question, but you could have asked that question. Is this ring activated or deactivated? And the
Well,
answer,
it's activated, so that means that
The answer is
prefer
activated?
Para ortho, but para is the best one because of the inductive effect.
and because it's activated ring, it actually reacts with bromine without the Lewis acid catalyst. You don't need the FeBr3 for an activated ring. And it's para because the ortho position is deactivated inductively, and the para position is not deactivated as much inductively, and it's an OP director. And then the other question is, what if you reverse the steps? What if instead of putting the acetic anhydride on and then brominating it, you tried to do it like this? And then the AC2O, how would that affect the reaction? Would it still work?
No,
It would work,
but
but
not how you want it to.
good luck stuffing at one bromide. Right? Because it's much more activated with an NH2 group than it is with the acetyl, because this lone pair is actually interacting with the amide as well. So stopping at monobromination is probably not going to happen. And you would actually probably make the 2,4-dibromo compound if you didn't protect it first. In this case, you're not working with a strong acid, so you don't have to worry about it forming an NH3 plus group and becoming a meta-director, but you do have to worry about it just being too activated and not being able to stop. Of course, the spectra that you would be looking at, you'd be looking for this distinctive pattern for a para-substituted benzene in the NMR that would tell you that it's para-substituted. And you should know what a para-substituted benzene looks like in the NMR, I hope. Maybe. Carbon NMR obviously has symmetry on this one and no symmetry on these two. So the fact that you only have 6 carbon peaks, right, also tells you that it's a symmetrically substituted one because these would have 8. So there's nothing in the analysis of the spectra and stuff from the lab that you need to do the lab for. It's just reinforcing those concepts. It should be a pretty easy lab, relatively speaking, especially since you don't actually have to run any of the spectra yourself. Since I ran them all. What's that?
It's kind of nice when nothing works.
Well, we could have done that lab, right? The GC mass spec and the IR and all. It's only the NMR we can't do. But we couldn't do it because we can't have more than 9 people in the lab at a time. That's why we had to switch to the A and B groups. Hopefully next year we won't have to switch to the A and B groups.
We can't have more than 9 people in lab at a time, but next year we're going to have 54 kids in one lecture.
48 so far.
Oh, 48. That's a
8.
lot less than.
The labs are 18, 16, and 14.
Oh my god.
Well, that's normal, right? Normally,
I mean, yeah, I guess.
normally the cap on the lab is 18 because everybody's got a lab partner in a hood. We can fit 20 except that hood 7 is not working. So as long as we still have 7 functioning hoods or 9 functioning hoods and another one doesn't break, we can still have 18 people. If we lose another hood, then it goes down to 16. And if we lose another hood, then it goes down to 14. Either that or we just start taking the alarms off and pretending they're working.
We did for mine.